Alright friends, welcome to 5-3's Notes Completion. It's time to get sassy, people. Woo! There's a lot of sass in this class, that's why I like it. So let's get sassy, let's see what's up. What can we conclude about two triangles when we know that two pairs of corresponding sides and a pair of corresponding included angles are congruent? Well, let's see. SAS is a nice little abbreviation for when we have side, angle, side in a pair of triangles. So now in the last section we talked about you needed all 6 parts of one triangle to match up with all 6 parts of another to say that the triangles were congruent. But as promised, we're going to learn some shortcuts, and sassafras is the first one. So the Theorem 5.5 tells us if two sides and an included angle, so now this is the key thing, the included angle is the one in between the two sides that you have congruent. So if that's the case, then the two triangles are congruent. So just as depicted here. So you have a pair of sides matching up, another pair of sides matching up, and the angle in between them. The angle, that's what we refer to as included. It's the one in between the two sides that were congruent. So you got to be careful. You can't have a situation where you have an angle, then a side, then the other side over here. This would spell something very unfortunate with an A and two S's. And we don't like to swear in geometry class. Often. No, but anyway, this would basically amount to angle side side, and that is not a valid way to prove that triangles are congruent. Alright, so the angle has to be included in between the two sides. Alright, hang on one second here. Let me show you the case where angle side side actually does not work. Alright, so say I have an angle congruent to an angle, a side congruent to a side. So now check this out. The third side, if I draw it over here, for instance, to complete this triangle, and say I take this same length and I draw it in like this, so that those two lengths would be congruent. Alright, so then I wouldn't need this extra part right here. This is basically, when you guys take pre-calculus, the ambiguous case, something that your pre-calc teachers will talk to you about, but this is essentially why you can't have angle, then a side, then another side. Because that third side, there are two possibilities of where it could be. So it doesn't guarantee you that clearly this triangle is not congruent or the same as this triangle. So an angle followed by a side followed by another side does not guarantee us triangle congruence. It's got to be set up like this, where the angle is sandwiched in between the two sides. It's kind of like these two sides hinge on that angle. So if they have the same hinge in between them, then the length of that third side, they would have to be the same. So that's why you can get sassy, but not ASS. All right, so now let's use the SAS congruence theorem. So two column proofs. You know there's two column proofs coming at you in this chapter. Let's take a look. First step is always given. So in this situation, we are given BC congruent to DA and BC parallel to DA. So they've marked the picture for us. They won't always do that. Sometimes you may have to mark that on your own. But in this case, they did it for us. Let's clean this up there a little bit now. Alright, so let's see what we would do. Okay, so trying to show two triangles are congruent, they gave us a couple important pieces. So we marked that in the given. So you know you're going after SAS, so you're going to need 3 different elements. Well, they came out and just straight up gave you one of them. So there's one of your sides. So now we have to get the other two things. And let's take a look. When we talked last section about when we see parallel, BC is parallel to AD. You can pretty much use your transversal and you can outline or highlight the two angles that are going to be congruent as a result of that by alternate interior. So our second step is going to be to take the parallel given information and turn that into a pair of congruent angles. So now I'm going to say angle BCA congruent to angle DAC. Alternate interior. You'll alt int, and there's your second letter. So there's S and an A, and that all comes from your given. So now where are we going to get that last S? Well, of course, we talked about the reflexive property last section. So we're going to use it. So AC is congruent to itself. If triangles share a side like this, then you know you're going to be able to mark it reflexive. So the reflexive property going to be used a lot this entire chapter. All right, now once we have enough to say side, angle, side, now we can get sassy with this thing. Then we can say that the two triangles are congruent. So just list them as they did. Triangle ABC congruent to triangle CDA and SAS. That's going to be a reason why the triangles are congruent. So there you go, guys. A very important example illustrating how SAS is all you need. We didn't need to say that the other two angle pairs were congruent, or the last pair of sides was congruent. Once you can get sassy, that is enough to say the triangles are congruent. All right, pause the video and try this one. All right, back again. So we know we're going to need our two columns, our statements, and our reasons. The first step is always the given information. So all that stuff goes there. Okay, now we have to interpret some of these things here now, because when they say B is the midpoint, let's take a look at that first. Of AD. B is the midpoint of AD. So AD is down here, B is the middle. So that tells us that AB is congruent to BD by the definition of a midpoint. So if they say midpoint, you're going to say midpoint. Just think of it like that. You have to use that to justify why a pair of segments are congruent. So now we got, there's a letter, there's an S. Now these right angles, they also tell us that these two angles are right angles. Okay, that's a very important piece of information. This is starting to get a little yucky up here. All right. So now, because they are right angles, we know that all right angles are congruent, so I can put these two angles equal to each other. So, angle ABC congruent to angle DBC by the definition of right angles. Some books will say all right angles congruent. I like to keep it the same with the definitions. So they said midpoint, you said midpoint, they say right angles, you say right angles. Definition, definition. So now you have two pieces of the puzzle. And of course, our old friend reflexive is going to show up again. CB is congruent to itself. They're never going to give you the reflexive property. It's so easy though. It's basically like giving it to you whenever they show you a picture of triangles that share the same side. And now you have enough to get sassy. There's your three pieces. S, A, S. Now just don't even overthink the order of the letters. Just go right with what they did. Triangle ABC congruent to triangle DBC. And our new friend, sassy. Sass. Alright, moving along. Using SAS properties. So different shapes are going to contain SAS inside of them, various situations. An example 2 is an illustration of that. In the diagram, we've got QS and RP passing through the center of the circle, so aka they are diameters. What can you conclude about these two triangles? Well, we know that radii are all congruent, so that's just lovely. So MR, MS, MP, MQ are all congruent. And then, of course, you guys are getting really good with the vertical angles. So through vertical and radii, definition of radius, you know that the two triangles are congruent by SAS as well. And same with the monitoring progress question. What can you conclude about PTS and RTQ? Well, they gave us parallelograms we'll see this in chapter 7, that the diagonals of a p-gram bisect each other. So you got that and you got that. And then of course, you got your vertical angles here also. So they're going to get sassy as well, thanks to vertical. And vertical is a big one. You're going to use that one almost as much as you use the reflexive property. All right. Same type of thing here. The wings of a paper airplane have two congruent sides and two congruent angles. Use SAS to show it. All right, well, simply put, now you're going to have the reflexive property, and then that's going to give you SAS as well. So various instances that will get you into that situation. And then wrapping things up, let's go ahead and try this proof. Pause the video here, and then we'll call it a day, my friends. All right, picking it back up. We've got our statements and our reasons. First step is always the given. Second step, so all that stuff goes there. Okay, now, just like we talked about earlier, they say midpoint, you're going to say midpoint. Now this is cool because C is the midpoint of AE and BD. So it's going to cut both of these things in half. So when it's the midpoint of AE, that gives me AC congruent to CE. And it's also the midpoint of BD, so it's going to give me BC congruent to DC. So you've got two different midpoint statements here because of the word and. It's midpoint of both of those things. So our first one, we're going to say AC, in no particular order on these two, AC congruent to EC, definition of midpoint, and BC congruent DC, also by definition of midpoint. So they set it up here a couple times, so you're going to bring it down here a couple times, thanks to the word and. Now, don't forget your vertical angles in the center there. So angle ACB congruent to angle DCE, vertical. Oof. Pen is sloppy today, my friends. And now you have enough to say triangle ABC congruent to triangle EDC by SAS. So this section devoted entirely to SAS. You will learn some more shortcuts next week, but for right now, we're just getting sassy, my friends.